video is going to feel a little bit confusing at first, so you may want to watch it a couple of times to make sure you understand it correctly. What will commonly happen for you is you will have some expression in C where the variables can be of several types. And there are certain rules that the C compiler uses to decide the type of the final value that is being computed, and the value itself can be very counterintuitive if you don't understand the rules that the C compiler is using. So, demotion and promotion from a smaller variable in memory to a bigger variable in memory, these are two common rules. Let's quickly walk you through some examples of what can happen when you don't understand these rules. So when you try int a equals 2 by 3, what's going to happen is that the right-hand side of this expression is going to be evaluated. And since you have 2, which is an integer, being divided by 3, which is an integer, the value of this is going to be 0, which is going to be stored in A. So A becomes 0, and there's neither demotion nor promotion because the RHS value was an int and it was stored in an int box. Next, we see an example where somebody says, well, I want a decimal value. So they say float A equals 2 by 3, but when they actually evaluate this expression or this assignment, what they see is that A is actually stored as 0.0. Now, why is this? This is because the right-hand side is still evaluated as an int divided by an int, and when you have int divided by int, the result is also int. So this int is now promoted to a float, and it is stored in the LHS, but the RHS value that was calculated was an integer to begin with, and this was 0, so what is promoted, it becomes 0.0. Next, let's consider the example where we say we are going to divide an integer by a float. When you divide an integer by a float, so the basic rule is that when you perform an arithmetic expression with one that's an int and one that's a float, then the result ends up being treated as a float. It is promoted. So in this case, the RHS is promoted to a float, which takes the value 0.66. But then you put it in an int box, and now it is demoted, and it is stored in the variable A as 0. So you had a promotion, and then you had a demotion, and the end result becomes storing it as 0. Now, these are 3 ways of trying to store 2 by 3 in A in a way that stores its information. All of them failed. What is the correct way of doing it? Well, here's one way of doing it. You say float A equals 2 by 3.0. Now, in this case, the implicit conversion that happens on the RHS is that an integer is divided by a float, and the result is a float, and this float is stored in a float-sized variable A, and so it sets the value of A to be 0.66, which was the intent of the programmer. You can also see that there are limitations to how well this can be done. You can say, I'm going to put A equals 9 by 2, and you will end up getting just A to be 4. You can try and say float A equals 9 by 2, and again, you will just get A to be 4.0. So you have to be careful and ensure that the RHS evaluates as a float before trying to put it in a float box. Otherwise, you will end up getting all kinds of truncations that you did not expect in your logic. So the key principle to remember in that is that during demotion or promotion, the value of the right hand side does not change. It is only the data type of the right hand side value that changes to the data type of the LHS value. If you remember this rule, then you will know the limitations of how you can combine variables of different types in expressions. But how can we work around some of these limitations? This conversion that we saw on the previous slide was implicit. You can also do explicit typecasting to ensure that these conversions are reliable, and when you are unable to do a conversion, you know explicitly that the logic of your code is going to get broken. Automatic conversion is done by the compiler. Explicit conversion is done by us. Let's look at an example of how this can be done. So I can say int k equals 5, and then I can do an implicit promotion of the value of k to be stored in x so that x becomes 5.0. I've converted the integer's value into a float value using the implicit conversion capabilities available in the C compiler. But this approach can be flawed. Look at what happens here. We do an implicit conversion again, trusting the compiler to get the job done for us, and it doesn't work. The RHS evaluates to 0 because k is an integer and 10 is an integer, and then you try and put it in a float box and it goes there, but it goes as 0.0. So what you can do is you can do an explicit type conversion. You can say, I want the float version of k to be divided by 10 on the RHS. Now look at the brackets, what they're doing here. This inner bracket is covering this statement float. The syntax here means I want a box that contains the value of k as if it had been declared as a float variable. That value is divided by 10. So now you have a float being divided by an integer, which gives you a float, and that becomes a 0.5 value, which is then stored in Z. So with explicit conversion by typecasting, you are able to save your information and push it into your new declaration. You can also do this without typecasting, as we saw on the previous slide, by just converting this value into a float rather than keeping this as an integer. So whatever gets the job done. Remember also that when you are assigning values, the computer always calculates the RHS. It always evaluates the RHS to its complete extent before trying to do the assignment. We will look at this particular detail in much more depth when we start looking at precedence and associativity a couple of lectures down the line. Let's work through an example program where we first show you how the absence of typecasting breaks the logic of the program, and then we'll show you how using typecasting saves the day. Now, when you look at this code executing, you see a clear issue. You have this marks divided by total, where marks is an integer and total is an integer. And when you divide, you get 0 times 100, which becomes 0. And so the compiler prints out 0 and you don't know what to do. Now, instead, what you can say is, I will typecast marks such that I will get, instead of marks, the float version of marks in this expression. So that float divides by int gives me float, which multiplied by 100 gives me a percentage, which will be some value. And so typecasting saves the day. Next, let's look at a situation where typecasting actually gives us bad results. So here we have this integer x, and we are saying that we'll set the integer y to the value of int x. So x is a float. We typecast it to into y. So this becomes a demotion. We get y, and this does the job. This is what we expected. But now we look at this. This is float x, and x is set to e to the 50. Now here we have a problem. The problem is that x is too big to store in an int box. So even though float can represent this, when I try to typecast this into an integer, the integer box breaks. It's too small to store such a big value, and so I get a garbage error. I get a garbage value. So typecasting will work. In this case, the compiler will have no objection to it. It's just that you can get errors when you're trying to convert a smaller data type to a larger data type, or a larger data type to a smaller data type. You can get unexpected results, and then you have to essentially think deeply about the range of the data type that you are trying to store your result into, and the underlying representation of information in that data type that is helping represent that value.